I'm going to start by talking about next week's lab, which is Shazam, and I'll do a demo. Let me also mention that you will have another homework assignment due next Friday. It's not on the website yet, but I plan to hopefully get that up today, and I'll put a note on Piazza when it's up there. And the lab write-ups are due tomorrow, as usual. Every Friday, one or the other is due. Okay. So first of all, let me hope that this Shazam demo works. It worked when I did it in my office, but I've played with it since then, so we'll see. All right. So I have MATLAB open here. What I've done just a minute ago was I trained. Okay, well, first of all, let me review what Shazam is. Many of you may have this app on your phone. The purpose is that you can turn it on when there's music playing, and it will identify what is that song. It'll tell you the name of it, the artist, all of that stuff. So we're going to do the same thing, and the way Shazam is actually built, let's see, is using the Fourier transform, in particular the spectrogram, which is what you used in your last lab. So you're all familiar with this now. Let me first demonstrate just the Shazam working. I hope it works. All right. So what I've done here, so what we've done is we've trained Shazam on a list of 7 songs. All right. Of course, to build a functioning app, you would want it to have many, many more songs so it can actually identify them, because it's only going to be able to identify those 7 that I've trained it on. What I've written here is just a little script that will record using the microphone here, and then it'll run it through Shazam and say, what song is that I'm playing? I'm going to try playing one of the songs from my phone, because if I played it from here, you might think I'm cheating and that it just knows which song because the software told it. So let me do that. So I have some of the songs here. All right. We know this song, right? Hotel California. So I'm going to run this. It's going to record for 10 seconds, and then it's going to try to guess the song. It's just loading in the files right now. Just wait a minute. Ignore this. There we go. I got it. Whew. Should we try it again with another song? To make sure it doesn't always say Hotel California. It has Hotel California. It has the 3 Windows demo sound files that we've used in this class before. Has 2 other short songs that I don't know where we got them from. They were used last year in the lab, so I just used those. You put in whatever you want. Yep. We could retrain it on whatever MP3 files you want. All right. There's a song called Dreamweaver. We'll try that one. So I'll just play it somewhere in the middle. Got it. See, it says Dreamweaver. All right. Well, should we try another one? We can even shorten the. I just have to change this number right here to say how many seconds to record. Of course, if we record fewer seconds, it's more likely to make a mistake. Try a song that's not there. Yeah, it'll pick one. So what about? Here, I'll do one more. But I want to mention, first of all, this code is not the best we can do. This was provided by past students and TAs, and it works. So I'm using it for the demo. But reading through it, I can see things I would change to try to make it work better. I hope all of you take on the challenge while you're doing the lab. Because, you could, of course you can push it to the limit no matter how good your code is. You can shorten the duration. You can consider adding noise. We probably have some noise in the room that's being recorded. We could add more and see how good of a job it does. And if you change fundamentally how it works and tweak it here and there, you probably can get it to perform even better than what we have. So, all right, let's do one more here. Oh, this. I shouldn't talk while it's going. It got it anyway. I was going to tell you the name of it is Sleep Away. All right. Should have told you that beforehand so you'd know if it got it. So I even talked and it still worked. All right. Okay. Should we shorten it and see if we can get it to still work? I didn't bring my keyboard this time, and the keyboard's not popping up on here. Where is it? Too bad. I cannot type. Unless I open this thing up, and it's going to slow us down. So I won't do it. Okay, but we could have when I was trying it in my office, I could get 5 seconds. It would usually get it right. Okay. Okay, so how does this work? Well, first of all, let me retrain it because while it's being trained, it pops up all these nice graphs, and I just want to point out the graphs to you. So to retrain it, I just have to go into the, I just have to go in here and delete the 2 files that it creates when it trains. So let's delete. Okay. Now let me come over here and do the training again. So what it's doing now is it's reading through. I have just a directory called songs, and anything I put in there, it's going to go grab all those files and go one by one, pull out fingerprints, things that we're going to be able to use to identify them. And these graphs are just things you'll create when you do the lab to help you understand what's happening. So it's doing 2 graphs for each of the 7 songs that I have in that file. And we'll look at them once it's done. In fact, let me grab one. Okay, so you might recognize this is the kind of looks like the spectrograms you looked at. Although your spectrogram in the lab was a telephone signal that had only a couple of definite tones at a time. Okay, music is much more complicated. It has a lot of different frequencies in it at each moment in time. So this is the spectrogram of a song. Now, let me mention a couple of things. In fact, I will, gosh, I really need to be able to type. All right. Okay, in the lab, when you type, you use the command spectrogram, you give it a sound signal and some parameters, and it gives you frequency versus time, right? And it shows you the colors of the spectrogram are showing you the magnitude of the Fourier transform localized at that region of time and at that frequency. First of all, let me just point out the built-in function will show frequency horizontally and time vertically. I'm not sure why it does that because it's much more conventional to show time horizontally and frequency vertically. And here, usually you would have frequency going from 0 and then up to the maximum. Here it's flipped because whoever made this code flipped it. That's what I tried to change on the way over here and didn't successfully change it. So basically, the red is just where there's a lot of frequency. Now, this looks really chaotic, but the thing is that this is a whole song. It's over 300 seconds. It's like 400 seconds. You would really want to zoom in to a shorter period of time to see something interesting. And now you see what looks like maybe some structure, frequencies changing with time. They kind of move together because instruments have harmonics. So this looks like, of course, everything's flipped upside down. Sorry about that. So this is an instrument that's making a sound and then goes to what is actually a lower frequency, moves down some number of notes. Okay, and all of these red lines move together because it's the same instrument, and these are harmonics of that instrument moving together. All right, so we see some interesting structure to this music once we zoom in. All right, so let me first ask you, how would you do Shazam? Let's start as naive as possible. How would you try to identify whether two sound files are the same? Okay, now I'm really saying start as naive as possible. What you might do is you might say, well, how do you identify whether two files are the same or different? You just check, you have the operating system check if they're the same, okay? Or what we could do in MATLAB is we could take the sound that we want to identify, we could take the song, and we could check if they're different by subtracting them, all right? Subtract them and see if we get 0. And now we may not get exactly 0, but see which one gets closest to 0, okay? What would be some problems with doing this? What?
It's possible you might only have like a section of the song instead of the entire.
Okay, so the first problem is we have no idea where the time shift is. You know, we recorded something, there's no way that it's just going to accidentally line up exactly when we do the subtraction. So that's the first important thing, is that whatever we do to match, it better not matter how much we shift in time. It better be able to fix that. And to solve that problem, what Shazam does is basically look at every time shift. Okay, we'll do it in a way that's a little computationally nicer, but we'll consider all time shifts and see if we find a good match. Okay, how about some other problems? Yes?
You don't know what is going to happen to the amplitude, and in particular, there might actually be some uneven frequency response of the speaker that's playing the sound.
Okay.
So we don't know if the waveform might get distorted.
Exactly. And we should expect it to get distorted. So if you actually look at the plot of the original music in time, and we look at the plot of our recorded version of it, okay, and we line it up perfectly, they won't look at all the same, pretty much. The reason is this. As was mentioned here, well, we don't know how the amplitude is, so we'd have to do some sort of amplitude adjustment. But on top of that, echoes, there are various echoes that are going between the microphone and the speaker. In addition, the microphone's not perfect and the speaker's not perfect. But what that amounts to is that the frequency, as was just mentioned, the frequency response, and this is something we'll get into much, over the weeks coming. When we talk about filtering, we'll address this more carefully. But because of this process of going from the sound file on my phone to being recorded by the microphone, different frequencies will be amplified more than others, and the phases of these signals will be different. And when you actually look at it, it won't look at all the same in time, although it'll sound the same pretty much. Now, why is it that it sounds the same? You did an experiment in your first lab with sound, or actually maybe not. It was an extra part. Did anyone do the extra of week 1 lab? If you create some sound, okay, and you then go changing the phase of these sinusoids, it doesn't sound any different. All right? So our ears don't really pick that up. We don't pick up the phase, meaning the shift of the sinusoid. We just pick up how much of each frequency there is, which is partly why we find it convenient to plot only the amplitude of the Fourier transform. Remember, the Fourier transform, this is a version of the Fourier transform that's being plotted here. Those are complex numbers. But what I'm actually plotting here, and we'll talk more about that in this lecture, is the magnitude only. And part of the reason why we do that for many signals is because, for example, our ears are sensitive to the magnitude, but not really the phase. Okay. So that would be probably the biggest issue, is that these shifts, the different sinusoids shifting by minute different amounts, are going to cause that method to not work at all. And then one other thing is just that there will be noise. Okay, we have to expect imperfections anyway. They have nothing to do with what we were just talking about. And so we want to pull out some features that are robust to noise. All right. So, so it turns out that the Fourier transform, so what we actually pull out as features is not, we take the spectrogram and then we look for local peaks in the spectrogram. Okay, so these plots over here are the locations of local peaks. I would have to get figure 9 to, actually let me just do figure 11 and 10. All right, so these go together. Oh boy, that one looks really crazy. I thought these went together. It's hard to tell. In your lab, what we'll have you do is plot these on top of each other to check that you've actually found local peaks. Okay, so we write code that goes through and checks the magnitude of the Fourier transform. Is it greater than everything in some small surrounding area? And then we tag that as a local peak. All right, and we end up with something that looks like this. All right, then we do one more thing to try to get rid of our sensitivity to noise, and that is that if in regions of the spectrum in the frequency domain that are low amplitude, this happens a lot, let's say in the high frequencies, the noise could easily affect those peaks a lot. So we'll actually add a threshold. So after you've identified all the peaks, you then actually add a threshold and say if the amplitude is not bigger than a certain amount, ignore it. All right? And that helps us be more robust to noise. So what you've ended up with is the fingerprint of the song. And the reasoning for it is that this should be fairly robust to the things we've talked about. So aside from time shift, of course, this will be affected by time shift. But it won't be affected much by the types of things, the slight variations in the frequency domain that happen from the echo path and from the imperfections of the microphone and the speakers. All right, those probably will not move the local peaks, or at least not too many of them. All right. So then the final step would be very simple. If we wanted things to be simple, we would just take our songs, and this is all we've now stored of the songs, or these binary matrices. And we would take our clip of music, which is probably much shorter. We'd do the same thing to that. And we'd go along and shift it at every possible shift in time, and we'd see, can we get it to match up? Can we get the dots to match up very well? Maybe subtract them from each other or something at this point. And find the best match. Out of all the songs in the database, where can I match this clip the best? All right? And that actually, I believe, would work very well. In fact, if I've been intending to try that, I just haven't gotten around to it. And if some of you want to try it, if you find time in the lab to do that, then it would be interesting to see, does this work better? Does it work a lot better? There's a reason why that's not what's done with Shazam. And that is that it would take too long. I believe that's why. To be simpler, you have to, I mean, if you're going to compare, huge database of songs, you're not going to want to do that type of computation. So instead, you do the following, and this is also what you'll do in the lab. You go through here and you try to summarize this fingerprint in a much more concise way. So you go through and find all pairs of points that are close enough together in both time and frequency. All right, close enough, you set some threshold and you say, just look for pairs of points that are within a certain vicinity of each other. And then record each of those pairs in a big table. So you just save the exact time and frequency of each pair. In a table, you go sort it, you stick them in this table, and then you do the same thing for the clip you're trying to identify, and you use that table then to try to find the best match. And there's a way to do that, which you can read more about in the lab write-up. It's referred to as a hash in the original Shazam algorithm and also in your lab write-up, hash function, because what's actually done, if you do this in the industrial setting, you don't make a table that's big enough to store all possible pairs. Okay? You have a table that's too small, and so the location to store these pairs of frequencies and times, they collide with each other. Several different time frequency pairs might be saved in the same list in the table. And that's a hash function generally does that. It's a mapping from a bigger space to a smaller space, where you get a lot of collisions. All right. Now you don't want the collisions, but the reason for doing that is to have a smaller size table to store. Okay. And it turns out that even though you can have collisions and that would possibly lead to problems with Shazam, it doesn't lead to too many problems as long as your table's big enough. So even with these little even though you sacrifice performance potentially for a software that runs faster, you don't sacrifice too much. It still works very well, and it actually can run on huge databases. All right. Any questions about what we've talked so far? Let's see. Anything else we should say about Shazam before they go in the lab next week? Really? No questions? Ask them now, because this will be your job for the next couple of weeks in the lab to get this working. I don't mean next couple of weeks entirely, but for the lab time the next couple of weeks. Okay, great. So let's talk again about, we're going to do the Fourier transform. We're going to do the FFT. We'll arrive at that by first. Well, we'll get there eventually. Okay, so suppose you have some vector. I'm going to call this, say, x equals the following. All right, so this vector is of length 8. Suppose we got this vector from something. Maybe it was a recording. Maybe we produced it ourselves. But to us, it represents a signal. All right. So to show that, I'm going to plot this thing. And I'll suppose that this vector goes from time 0 to time 7. And it's like the following. Oh, let me use another color. Okay, it's these 8 points. Now, maybe this vector came from an actual continuous time signal that was sampled. Okay, that's what happens when we are looking at sound signals that have been sampled, and then we end up with a discrete time signal. So even though this vector should be interpreted as a discrete time signal, I'm going to just draw in something to say, okay, maybe it actually came from some continuous signal. Maybe that signal looked like this, and then maybe it was sampled. But at this point, it's just numbers, all right? We can't get back. I mean, we may not be able to figure out from these numbers what the actual continuous time signal is. We didn't record it all. We just recorded these numbers. Also, this may be part of an infinite length signal. And maybe we just recorded part of it. All right. But at this point, we can use the Fourier series on such a vector as if that vector was. And so the way to do that would be to imagine that this vector is one period of a periodic signal. Okay? So if we interpret that vector as one period of a periodic signal, that interpretation makes the periodic signal look like this. And then it would repeat, right? And so forth. So its period is, so we have like this, 0, 1, 2. Here was 7. Here's 8. Here's 9. Okay, so its fundamental period is actually 8 here. Just so you can see that better, I'm going to just do this. Okay, this we call the periodic extension of a signal. That is, take what you have, this finite duration signal, and repeat it over and over. Okay, so well, great, because any periodic signal, the discrete time Fourier series is well defined for periodic signal, right? So then let's take the dt fs, and by that I mean discrete time Fourier series. Okay. So I will go back and I will label this vector the way we usually label discrete time signals. We'll call this one x at time 0, x at time 1, and so forth. X at time 8. All right. And we know the formula for the Fourier series. I'll just write it here. AK equals the sum from n equals 0 to 7. K over 8, I'm going to combine the 2 and the 8. So I pi k over 4 n. All right, so here's the Fourier series. Here's how you calculate the Fourier series coefficients. So in other words, just to be explicit here, we would have that it should be 1 over 8 out front. Right. Okay, so we would have, for example, that A0 is just 1/8 times the sum from n equals 0 to 7 of xn, because when you plug 0 in for k, the exponential goes away. So that's interesting. A0 is just the average, right? And let's just write out one more. A1 is this. I pi n over 4, and so forth. Okay. So these are the coefficients of our Fourier series. To completely define the Fourier series, we also need to not only you would give the coefficients, but you would also say the fundamental period. We'll see that in discrete time that's actually redundant, but we would say n equals 8, and the coefficients are these things. Now, these coefficients are complex numbers, but if we want to interpret them, if we want to kind of have some intuition about what those numbers mean in the signal, of course we know mathematically that they're the coefficients of the exponentials. But we can think of this as the frequency domain. And each of these coefficients are a coefficient for a given frequency. What would that frequency be? This one here would be f equals 0. This here would be f equals... Now, frequency, remember, sinusoids, we have a way of reading out frequencies from sinusoids. Think of this complex exponential as a sinusoid. We would have e to the I 2 pi f would be times time. 2 pi fn would be a sinusoid of frequency f. Okay. So the frequency of this sinusoid, the f here, is 1/8, right? It should be 2 pi n over 8. So the frequency is 1/8. Okay, and so forth. And so now we can interpret these coefficients as the amount of signal, both magnitude and phase, at these frequencies. 0, 1/8, 2/8, 3/8, and so forth. In discrete time, how many of these do we need to fully recover x? We need 8. So in continuous time, you might need infinite number of them. But in discrete time, you never need more than the length of the vector. All right, we'll talk more about that in just a moment. So basically, we only have to go up to A7. All right? The frequency there would be f equals 7/8. All right. Out of curiosity, what happens if we try to calculate it for k equals 8? All right. Let's try that. Of course, this is not needed. So we would get A8 equals 1/8 sum and we'd have 8 over 4, which is 2, right? Of course, we can pull the n out here. All right. And this is e to the negative I 2 pi n. This is e to the minus I 2 pi to the n. What's that? What's e to the minus 2 pi? It's minus I 2 pi. 1. Right? So this is 1 to the n. It's just 1. So this thing equals just 1/8 sum n equals 0 to 7 xn. It's just the average. It's just the same as x0 as a0. Okay? For demonstration purposes, I will show you that a9 equals, what do you think it's going to equal? a1. It's going to equal a1. Let's just check. So we would do e to the I pi, it would be 9/8 n, but we can pull out an 8/8 and a 1/8. Okay, so this here is just, let's use blue. This is e to the minus I 2 pi n times e to the minus I pi 1/8. Oh, whoops, this should have been 4. Right? Okay. If I make mistakes, please tell me. All right. E to the minus I pi 1/4 n, right? And this first term is just 1, as we just saw. So it's exactly, we would replace this with 1/4 instead of 9/4. But that's exactly what we had here. Okay, so this will also be the same. A1. In general, the coefficients would be exactly the same if their indices differ by the period of the original signal. This is what's known as aliasing. It's very important, and we will revisit it when we get to sampling. But let's first talk about it right now. naturally you lose something taking a continuous time signal and only storing it at the integers. In other words, sampling a continuous time signal and making it a discrete time signal, you must lose some information, and here's what you lose. Two sinusoids can be exactly the same in discrete time, even though their continuous time formula does not look the same. In discrete time, they are exactly the same signal. So here's an illustration of that. Okay, here's a sinusoid. And actually, here's two sinusoids. And yet, when you sample at these integer values, they're always equal at the integers. Therefore, therefore they are the same discrete time signal. In discrete time, all you have is the value at the integers. This in-between stuff is not even part of the signal in discrete time. So if they're the same at every integer, they're the same discrete time signal. Now, I can adjust the frequency just to show that this doesn't just occur there. Oh. No, maybe I have to. There we go. Oh, what was that? So you see that what I'm doing is I'm adjusting the frequency of the purple one, and then it's always showing me which blue one is the same. It's giving me another sinusoid that's exactly the same. All right. In fact, there are going to be an infinite number of sinusoids that we could find that go through these same points. And so these sinusoids, in effect, they're aliased because there's many names for them. We could write them down. They can look like different formulas on paper, but they're actually the same thing. All right. In fact, understanding which sinusoid's alias is very simple. And that's something we'll start to understand right now. And that is the following. Rather than looking at these as trigonometric functions, as sines or cosines, let's look at the complex exponential, because understanding which complex exponentials are the same is extremely simple. We've already done it, basically. That's this. E to the I 2 pi f1 n equals e to the I 2 pi f2n if and only if f1 minus f2 is an integer. Now, you have to, I should be more clear mathematically here, but I think in context you know what I'm talking about. I'm talking about these as signals, as discrete time signals. So what that means is, I'm saying these are the same signal. That means they're the same for every integer n, right? So these two signals are the same. That implies for all integer n. Okay, because the integers n are saying, are the integers, that's the domain of our signal. So they're exactly the same for every n. And now we can see why this is true, at least the if part of it, that if f1 minus f2 is an integer, then we can do the following division. We can say e to the I 2 pi f1 n over e to the I 2 pi f2n equals e to the I 2 pi and voila, we know that that equals 1 if everything here is an integer. So if f1 minus 2 is an integer and n's an integer, then this is just an integer times 2 pi. All right, so it equals 1. So understanding aliasing, here's maybe our first benefit we see by using complex exponentials. Understanding aliasing for complex exponentials is this simple. That's all it is. Now for sinusoids, you have to, there's other possibilities of aliasing besides their frequencies differing by 1. The reason is that a sinusoid has two complex exponentials. And if you look at it carefully, which you will through the rest of the course, you'll see that you can alias even if their frequencies aren't differing by 1 because of just, one of the complex exponentials aliases with the other one on this side, and this one aliases with the one on this side. Okay, they like swap sides. All right. Okay, so that's what we're seeing here. We're saying, look, there's no reason to add in more Fourier coefficients than the first 8, because every other sinusoid that you'd be adding is the same as the ones you've already added. All right, and that's why we got the same coefficients here. So that shows you something interesting here. That says that in terms of if you're interpreting these as frequencies, that you only get to look at frequencies up to frequency 1, all right, or roughly 1, from 0 to n minus 1 over n. You can ask, what's the frequency content higher than that? That would be like Fourier series coefficients higher. It's just going to repeat. And we'll see this. Next week when we talk about the Fourier transform, that you get this property that in discrete time it's going to repeat eventually. Right now in the Fourier series, where you just get hints of this. All right. The other thing is this. It's often the convention not to look at frequencies from 0 to 1, but instead to look at frequencies from -0.5 to 0.5. All right. And so what we could do is we can, of course, calculate Fourier series coefficients for negative k. And we'll find that because it's periodic, what's a of -1 going to be? Anyone? Yes, A7. All right, and a of -2 is A6. All right. And so if we want to instead observe the frequency content from -0.5 to 0.5, we should take our high end and we should plop it down at the low end. Does anyone recognize this from the lab? FFT shift. So we didn't really explain why you do this FFT shift. That's exactly what it does. If you say FFT shift of a vector, it just chops it in half and goes and takes the first half and puts it at the beginning. The second half puts it at the beginning. All right. But the reason is because the FFT, which we'll talk about today, is where did my pen go? The FFT is gives you the Fourier series coefficients up to, as I've demonstrated here. So it would give you A0 up to a of n minus 1. Where did I just set my pen? There it is. All right, the last thing is about this picture here. It may seem strange that I'm telling you that for discrete time signals, you only get interesting frequency domain from frequencies -0.5 to 0.5. Everything beyond that repeats. Because you might be thinking, well, you looked at Fourier transforms in your lab and you saw frequencies going up to thousands, right? Why am I saying it only goes up to 0.5 and -0.5? That's because discrete time signals are always, by convention, sampled at the integers. Okay? But if in fact your vector, you know that vector is meant to represent samples of a continuous time signal at a rate other than 1. In other words, if you didn't actually sample at 1 second, 2 seconds, 3 seconds, you sampled at some other frequency, and we'll call that the sampling frequency, then you should interpret these frequencies as actually the discrete time frequency times the sample rate. All right. So in other words, this would be f equals fs over 8, and so forth. And this would be f equals fs times 7/8. All right. And that's why you were able to look at frequencies up to much higher things, because you had sampled at a high frequency. Any questions so far about this? Okay, so far we've talked about the continuous time Fourier series and the discrete time Fourier series. Formulas were almost the same. One is meant to deal with continuous time signals, and one's meant to deal with discrete time signals. We've noticed some differences. The continuous time Fourier series can have an infinite number of coefficients that are all necessary to reconstruct. The discrete time Fourier series just has a finite number. These are all meant for periodic signals. Next week we'll learn what to do with signals that aren't periodic. We've also noticed that even though they're meant for periodic signals, you can just as easily use them for finite duration signals. And when you use the discrete time Fourier series on a finite duration signal, you interpret the finite duration as starting at 0 and going towards the end of its duration and repeating. Okay, therefore it's periodic. So there's sort of a easy mapping between finite duration signals and periodic signals. That's just their periodic extension. So we see that we can use the Fourier series for either one of these. Now, the DFT stands for discrete Fourier transform. All right. Now, in fact, the best way to think of this is that it is a discrete time Fourier series. So why do we need a new name? Well, for one thing, the DFT is what's used in practice all the time, and it has a just teeny difference from the discrete time Fourier series. The naming of discrete Fourier transform is meant to imply that both the in time it's discrete and in frequency it's discrete. All right, and we see that that's what happens with the discrete time Fourier series. In time, it's discrete. That's what it's called. It's a discrete time signal. But because it's finite duration, which implies that we're interpreting it as if it's periodic, we got that the frequency domain is also discrete and finite, and it's these things, and it's just the exact same length of numbers. It's the same length of a vector as the original finite duration signal. All right, so the discrete time Fourier series used on a finite duration signal, it goes by another name, the discrete Fourier transform. And technically, this is what you are using in MATLAB, because the command FFT is a fast algorithm meant to compute the discrete Fourier transform. Okay, so let me just talk a little bit more about this transform. So interpret your signal as a vector. Okay, so we have some finite duration signal. We'll write it as a vector. So x equals x0, x1, xn minus 1, transpose. Okay. And let's let, what do I want to call the output of this? I'll just use A since that's what I've been doing. So A will be the Fourier series coefficients. So the Fourier transform, the DFT just produces A of the vector A equals, let me say, DFT of the vector X. All right. And then X would equal the inverse DFT of A. Now, since we know the length of the vector, there's no need, I said in the discrete time Fourier series, there's no need to, you usually have to specify the period. However, in discrete time, the period is always implied by the length of the vector. So, implied period is n. So there's no need to specify that separately. In other words, when you call the DFT in MATLAB, you don't have to tell it the period of your signal with which to compute the discrete time Fourier series. It always just assumes you gave it a finite vector and you intend for that to be interpreted as the periodic signal, and that's the first period. And therefore, it computes the discrete time Fourier series. I keep saying it's the discrete time Fourier series because the difference between this and the discrete time Fourier series is so minute. And it's just the following. AK equals the sum of xi All right, so this is the formula used to compute the DFT. So what is different about this and the Fourier series? Yes?
Sorry, just to clarify, the indice is distinct from
Yes, good point. Let me, I do have I there and there, so let me make that M. Good. Okay, so let me make that M. Thanks. All right, so what's the difference between this and the discrete time Fourier series? Can anyone find it? What was that? That's all. It's just this. Moved from there. That's the only difference. Of course, it doesn't matter. I mean, if you're transforming and transforming back, who cares where you put the 1 over n? It doesn't make a difference in terms of how useful it is or anything. It's just a technical difference, hardly matters at all. There are reasons why people would like to put the 1 over n there. Maybe you'll understand them later when you think of this as there's yet a second way to interpret the DFT. I'm explaining that it's just the discrete time Fourier series with the 1 over n moved. There's a second way to interpret it related to the Fourier transform. And if you want that interpretation, then the 1 over n might be better here. Okay. So really, it's fundamentally no different. This is the Fourier series. Right? Okay, so then what is this FFT? Well, like I said, the FFT is just a way of computing the DFT. So first maybe we should write the DFT in a number way that's in another way than I've written it here, an equivalent way. So imagine that we do the following. X equals actually, let's do the forward DFT. So A equals a particular matrix times F. That matrix looks like this. And then let me do it for 4. I'll do it this way. I'll write it generally. E to the negative I 2 pi 1 over n. E to the minus I 2 pi 2 over n. Oh, I don't have enough room. All right. I've drawn a pattern. I'm not going to fill it all in. Times x. Okay, so this is just another way of writing these sums. I've already given you the formula for calculating A1, A2, A3, A0. And all I'm saying now is, if you want to calculate the vector of A0 through AN minus 1 from the vector of x0 to xn minus 1, you are just doing this matrix multiply. So notice this formula is just linear. So we should be able to express it as a matrix multiply. And if you recall how you multiply matrices, you take x as a column vector, and each row of a matrix gets multiplied by x. You take an inner product between each row of the matrix and x, and that becomes the first value. For the first row, that becomes the first value in this vector A. For the second row, inner product with x, that becomes the second value in A, and so forth. So we can just verify that this matrix that I've written here, this multiplication, is exactly this formula. Because notice this is saying A0, the first entry of A, should be x, all the x's added together. Well, what's going to happen when you take x and you multiply it by all ones? Take an inner product. It means multiply 1 by each value of x, add them all up. Okay? A1 should be x times a different number for each x. And those numbers should be, the first one should just be m equals 0. So this should just be 1. That's what this is, 1. The second number that you multiply by x sub 1 should be e to the minus I 2 pi 1 over n. That's here. That's going to be multiplied by the second part of n. And so forth. So this whole row, each one of these gets multiplied by one term of x and added up. That's what matrix multiply means. And we see we just have written out this formula in a matrix notation. All right. For brevity, people usually say, let me get an abbreviation here. I'm going to call W with two numbers, W sub r to the kth power. Let's just let that equal e to the I 2 pi k over r. Think of it as, think of w sub r is an rth root of 1, and k is just the normal exponentiation. We take w sub r to the kth power. But this just gives us a more brief way of writing this matrix. So we get actually that A equals, and it's just like, and here's the pattern. W n 0, W n 0, W n 0, n 0, W n 1, W n, whoops, minus 1, minus 2, and so forth. And then here it's like this. Dot, 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 dot. And that's how we fill it all up. Of course, the last thing the last row is going to be W n to the n minus 1. Oh, no, sorry, 0 here still. W n to the n minus 1. And because it's periodic, W n to the n minus 1 is equal to W sub n to the minus 1. Oh, whoops, sorry, this should be. This equals W sub n to the 1. That equals W sub n to the 2, so forth. So anyway, we have this kind of matrix. It's got a nice symmetry, meaning that if you transpose it, it's the same. All right. And this matrix is the DFT matrix. Of size n. Okay. So computing the DFT is just a matrix multiply. Now, how many operations does it take, roughly, to do a matrix multiply with height n? A square matrix of height n? How many operations does it take to do this computation? You can think of it as a matrix, or you can think of it as these sums. Either way, if you want to compute all the the DFT coefficients, approximately how many multiplies do you have to do? N squared, right? Because each one took n, and you have n of them. So n squared. Okay, so computing the DFT this straightforward way is roughly n squared operations, which means as n gets long, that's the length of your vector. Computing the DFT gets harder and harder. It doesn't just get twice as long when you go to twice as long of a signal. You get to 4 times as much computation. Okay, that was a sort of detrimental for use of DFT in signal processing decades ago. And so what was shown was you could Cooley and Tukey. Oh, I don't remember which one has an E. I shouldn't try writing names. Maybe they both do. All right. In 1965, I believe, was it 65 or am I way off? You can check that for me if you want. They popularized a fast algorithm for computing the DFT that doesn't take n squared time. FFT takes n log n. So this was a huge speed up. All right, because now you can really, using this algorithm, you could then take the DFT of very long signals. So this kind of revolutionized digital signal processing using fast algorithms for the DFT. All right, so that's why you get FFT, the fast Fourier transform, is the command you call in MATLAB. It comes from this type of naming. So And the key here, there's many ways to view this. Most people describe the fast Fourier transform as they describe it more algorithmically, and they have these beautiful butterfly graphs showing like what you multiply with what first and second and so forth. But there's a linear algebra way to describe it, and that's simply that this matrix, the DFT matrix, we can call, let's give some examples of the DFT matrix, and then I'll show you roughly what the meaning is of the fast Fourier transform. So let's say, let's look at the DFT matrix. Size 2, just for fun. Okay, so I will call this F sub 2 equals 1, 1, 1, negative 1. So that's the DFT matrix you use to multiply if you want DFT of signals of length 2. Okay, it's that simple. Okay, and for length 4, you would do the following. You do minus 1. Okay, I'm just filling in the actual numbers for these W's because we defined what W is, and for for K and R being things like a half and stuff, it's very easy to figure it out, and it's these matrices. Okay, so you're actually just doing matrix multiplies like this when you're asking for the DFT. You can try that in MATLAB. Create this matrix, do a multiply, and then compare that to the FFT. It should be the same. All right, now it turns out that you can write F8, which I'm not going to write it out explicitly here because now I'm going to get more complicated terms. But, it's an 8 by 8 matrix, right? 8, 8. But you can factor it as a product of 3 things. So it turns out that it's just a matrix that first looks like the following. 1, 1, 1, 1. All of these zeros in that little 4 by 4 square. 1, 1, 1, 1. Zeros, zeros. Then here you get 1 W8 W8 squared W8 cubed. The off diagonals of that 4 by 4 are 0. Okay, this is the first part. I'm going to have 3 matrices multiplied together. As ugly as that looks, that's actually a very nice structure, right? They're mostly zeros, and zeros don't take any time because you don't have to multiply them. Then the next matrix is this, F4, 0, 0, F4. Now this is actually an 8 by 8 matrix. Looks smaller because F4 is 4 by 4. Okay, and my zeros here actually represent a 4 by 4 matrix, all filled with zeros. And then lastly, you need one other matrix. It's just a permutation matrix. So it just does the following. It just looks like this. It goes like okay, so it's just sorting out everything else zeros. So I know you can't really read what I'm doing here, but basically, you have a 1 in location 1, 1. You have a 1 in location 2, 3, 3, 5, 5, 8. And then you go down here and you've got, or 4, 8. And then you go down here, you've got, I messed up. Yeah, 4, 7. Then you get 5, 2, 6, 4, 7, 6, 8, 8. Okay, and this just rearranges your input vector. So the matrix that'll do the 8 by 8, the matrix that'll do the DFT of size 8, because it can be written as a multiplication of these three, we can count up how long does it take to do this. And this isn't so long. This first part only is just rearranging a matrix. It takes no more than order n time to do. This one also is roughly order n time. It's actually 2n. You have 2n components here. So between this and this combined, it's only 3n amount of time to do that. And so then the question is, how long does it take to do a DFT of half the size? All right? That's going to be the bottleneck, is the amount of time it takes to do the DFT of half the size. But you can keep cutting in half. You keep factoring at each level. And because you have this sort of geometric shrinking of the DFT that you have to do, you end up with n log n rather than n squared time to actually do this calculation. All right? So there are many ways to understand the FFT, and this is just one. Again, this maybe wouldn't be the way that you'd first see it if you looked it up. You'd see all sorts of beautiful diagrams. But really, this is equally valid way of understanding why it speeds up the process. Okay. Last thing. Inverse DFT. Again, we can look at the formula for the inverse DFT, and we notice that A equals, again, it's a matrix. It's something times x, and it's just going to be the following again, Wn0, Wn0, Wn1. Now, in the forward DFT, it was a negative 1, and here it's a positive 1. Dot, dot, dot. Okay, same pattern as the forward DFT, except here we have a 1 over n. So in other words, this just equals, so f, if we call Fn this if we call Fn the forward Fourier transform matrix, and we call Fn inverse the reverse Fourier transform matrix, we would see that the inverse Fourier transform matrix is just 1 over n times the conjugate of the forward one. Okay, so they're almost exactly the same. Computing it forward, computing it backwards. So that's something you might try as well, is use, you haven't yet used the inverse DFT, I don't think, in any of your labs, but it's there. I think it's just IFFT will reverse the DFT. Okay? But in fact, you could have just called FFT again and then do the appropriate modification, divide by n, and it'll actually involve a reversal of time. Okay? But in fact, you didn't need to have another algorithm in there for the inverse FFT. The FFT already does the inverse FFT. You just need slight tweaks to it. Go ahead.
What if you wanted to do the FFT of a signal like 7, like with each notice with 8, you can divide it.
Good. So then you have to, there are modified algorithms for lengths that are not powers of 2. And one way to do it, well, actually I won't even try to explain how because I don't really know, but there are ways of the in-between. So originally the algorithm would be very fast for lengths of order powers of 2, which is why a lot of signal processing is designed to work on powers of 2 lengths. Okay, so you'll see like, especially older stuff will be like, let's have our window be, 512 length or something. And it was because the FFT would work fast on that. Although there are modifications now where I don't think it matters too much if you're off length. They can still take advantage of a lot of the speed up.